Hello everyone, I'm Nex and welcome to our 6th lesson, sequences. So first of all, it's important to know what a sequence is, and the answer to that is that it's an ordered list of numbers, where each number is called a term, and the belonging to the sequence is described or defined by a rule or a formula. So if we want to find out if a number is part of a given sequence, we can plug every needed number or value into the formula and then calculate if it is true or not. So let's give you an example. Odd numbers, even numbers, they're all a part of their own sequence. So the example here is even numbers, where 2 is the first term, 4 is the second, 6 is the third, and so on and so on. But if I put in a number like 13, can I confidently say that it is or it is not a part of this sequence? Well, for now I cannot, but in maths, or whenever you run into sequences on your exams or whatnot, you kind of can. You do need to find the formula or the rule for the sequence, but we will get to that in a second. First, we will define what the words we will be using today mean, so you can kind of follow along and not be lost. So, about terms, individual numbers, well, they can be either finite, so there's a limited number of elements. Let's say a sequence 1, 2, 4, 8 is a sequence where each next term is double the previous one, and it's a finite. More likely than not, we will be running into infinite sequences, because, well, they go forever, and it's easier to set a rule. So in my videos and everything, we will be working with infinite we will be working with infinite sequences. Series are a part of the next video's topic, so let's keep that separated. The sequence notation, these are the important symbols. A1 is the first term, and AN is the nth term. So later on in the video, I'm not gonna be using AN for the nth term, I'll just be having A, because using the subscript for n is kind of hard to do and switching back and forth between them. Plus, I will already clarify which n value we will be calculating for. Don't get lost now, it may sound confusing, but you will be able to follow along when we get to there. So, for instance, if I say that we're calculating the third term, we would replace the n with the 3. Next is the rule, or another word for a formula or an expression that describes the sequence. We can have either an explicit or a direct formula where you plug in the number of the term you want to calculate. So we use the n variable and we calculate the term we want directly. And the second one is the recursive one, or the one based on previous terms, which is super useful to calculate the next term in the sequence. However, we will learn how to get explicit formula from the recursive, or at least you'll be given all the knowledge that you need so you can do it on your own, which I think is also part of the mini-test, so I would listen along very carefully. Now, the types of sequences that we can have are, of course, the first one is arithmetic or geometric. These are the most base typical ones. So in arithmetic, we have a constant difference, so each next term is the value added or subtracted from the previous term, so we only add numbers. For instance, even numbers, 2, 4, 6, 8. The difference there is 2, and it's an arithmetic sequence. As for geometric, it has a constant ratio. So each next term is some r times previous term greater. So we multiply each of the terms with a constant ratio to get the next one. Don't worry, it may sound confusing, we'll get to that and explain it with the visuals. There's also other types, like Fibonacci sequence, which you may have heard of already. But if you don't know what a Fibonacci sequence is, it's basically adding up the previous two terms together to make a next one, like so. So if I add 0 and 1 together, we get a 1. We add 1 and 1 together, we get 2. We add 1 and 2 together, we get 3. We add 3 and 5 together, we get 8. 5 and 8, we get 13. 8 and 13, we get 21, and so on. So if we add any two consecutive terms together, their sum is equal to the next term. And funnily enough, the consecutive elements or terms are super good at predicting the conversion between miles and kilometers. Like, if we take this from 3 on, of course. If we take 3 miles is approximately 5 kilometers. 5 miles is approximately 8 kilometers. 8 miles is approximately 13 kilometers, and so on and so on. You can also do it on your own to check if it's true or not. It's a fun little fact. Later on, we will do more math behind the sequence itself, so you can see or test this for yourself. But for now, you can just see the table as a fun fact, if nothing else. Next up is alternating sequences, and they're easily recognizable by the alternations between positive and negative signs, as you see here. But they don't have to alternate exactly like this. This is just an example, as I saw, e.g., to show you that this is one of the ways they can. Basically, as long as there's some alternations going on, it's an alternating series. I'll show you one later, which doesn't even alternate between the symbols. It just alternates between addition and subtraction. In this case, it's just multiplication. You will see everything. I won't dive too deep into it, but I'll go enough so you can understand why it is. And then we have some more like quadratic and factorial, which I won't cover as much because even I don't... I think I went through my notebook from when we did this in school, and we had like 2 examples in like 6 years of math in which that we have covered sequences out of quadratic, factorial, and others, so it probably won't be needed. If it is, I'm sorry, but my video will not cover that. Now, let's start off with arithmetic series. Oh my god, arithmetic sequences. You may hear me switching between sequences and series a lot, because I originally intended to make this one video, but I realized, well, I kinda can't, because this video is gonna be kinda shorter, and that other one is gonna be a bit shorter, but together they're just too long for one of my videos, so I split them off in 2 shorter parts. So the definition of arithmetic sequences: they are a sequence where the difference between consecutive terms is a constant, which we'll be naming common difference, or marking with a lowercase d. Now, for an example, we have a sequence 3, 7, 11, and 15, and of course, since it's an infinite one, we have 3 dots. If we know it's arithmetic, or we want to assume to start solving, we take any 2 consecutive terms and take their difference. Let's say the difference between 7 and 3, although we could do the same thing for 11 and 7, or 15 and 11, but we calculated the difference is 4. So, I will first give you the formula, and I will get to how we got it after we use it, so you can see the origins if you want to know them. You don't have to for this video, of course. So the explicit formula for arithmetic sequences can be generalized as such, where an is the term at the nth position, a1 is the first term, d is the common difference, and n is the position of the nth term we want to find. Usually, in functions, you could try to solve equations like this, where you have a point that you know that it's on the graph, so you put it in instead of x and y. In this case, n would be the x and an would be y. Then calculate the rest. But here you can just calculate the difference between a couple of terms by subtraction. You know which term is the first one in the sequence, or the given one, and calculate the other pieces of information that you need from that. So you only need, technically, if you know what type of sequence it is, 2 consecutive terms, or 2 terms that you know that there are some places apart and you know exactly how many places. We will get to that later on, but that's just basically easier way to solve than it is to solve the functions in this regard, because you just need 2 points. Now, how do we get it? Well, let's assume that we start off with the first term formula, aka what do we know about the relation between the first term and the nth term for n is 1. So if n is 1, an is 0 plus a1. Since we don't know much more, we know for sure that an is a1 in this case, because this is the most direct formula we can use. Now for n2, formula would have to be slightly different. Assuming that we want to base it on the first term, we have to keep the first term in every further equation, expression, whatever you want to call it, formula. We have to keep it intact and only work on what we're adding to that term to make it simpler, basically. And to get the second term, you basically add the difference, which is always constant, to the first term. Now, for n is 3, we see that we have to add 2 differences. And if we kept repeating that, like for 4 or 5 or 6, we see that we always add one, let's call it level less than we have the n. So if we want to get second term, we use one difference added to first term. If we want to get the third term, we would have to add 2 differences to the first term. And if we wanted to get like 15th term, we would have to add 14 differences to the first term, which kind of makes sense because, well, it's a difference between the 2 stages. So if we wanted to make them as steps, like staircases, the first step is already elevated from the ground. And if we want to use that as the base, we have to have one less step from like nth step. So for instance, if a staircase has 100 steps and you want to start off as the first step, you technically have 99 steps in front of you. And these are the 99 steps. So the amount of additions to get an from A is n minus 1. I put the absolute value because that's the difference between 2 positions. So like we remember absolute values and equations, we use the absolute value as the distance between the 2. So in this case, in this context, it's the distance between the nth term's position and the first term's position. So hopefully this kind of makes sense. So if we plug this in, we get the formula. Now it's important to remember that if we start off at the later stage, we have to take away those stages. So for instance, if we wanted to start at the second term, we would have to take away 2 from n. This comes in more handy if the term we're basing it off is after the nth term. So for instance, we want to get the first term, but we're giving 15th, 16th, and 17th terms. So usually you would see m instead of p, but having m and n in a video where it's hard to understand me speaking, plus the letters are tiny, I just gotta mark it as p. So pth term and nth term. Now, either formula is fine, just make sure to apply the variables or the values correctly. So you make sure that you're consistent with applying an and n and ap and p. That's all that matters. One thing that is important to mention, while sequences may be similar to functions, since there is a formula that predicts how the next value will behave, they're not graphed the same, since each position of the term, aka the possible n value, can only be part of natural numbers. So n value is natural numbers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And therefore we cannot get continuous lines as a graph. Like we remember those smooth lines that curved and everything? Yeah, we can't get this here. But we do get a bunch of points that, if connected, would give us the graph that a function with the same formula would have. For example here, we know that the first term is 3, so a1 is 3. We know that the difference is 4, and we take n minus 1 as the nth term formula. Now we replace n with x and an with y, and we graph that in. So if we want to graph out the sequence, we get these 4 points. If we were to connect them, or just draw the function, as you see the red line represents the function, and the 4 dots represent the sequence, we see that they overlap. So if we were to connect the dots, or the points, we would get the graph. Now, the sum of the first n terms is called a series. So I did mention the sum formulas in the PowerPoint when I had the roadmap at the start of my channel, but I did realize a couple of weeks later that the sum formulas are basically formulas that fall under series chapter, so I decided to acknowledge this oversight and correct myself while on the topic to not be deceitful and that you can spot it early on in the video. Although it may be a small slip-up, I do tend to uphold myself to some standard of predictability and expectations, whatever that may mean to some of you. It's a big part of my video creation or something, so I'll just clarify this here. The sum of the first n terms will fall under the series chapter, which is the next video that goes up in 2 weeks. So yes, now let's solve some sequences before we go on to the geometric ones. For example number 1, we have to find the 15th term of the sequence 2, 5, 8, and 11. So we know that n is 15, a1 is 2, and the difference is, let's take 5 minus 2, which is 3. So this gives us the formula. First term plus n minus 1 times 3 is 2 plus 14 times 3. Of course, as I said before, I will use a instead of an because it's just simpler to write. And we have 2 plus 42, which gives us 44. So there we have it. 15th term is 44. If you don't trust your math, you can always graph it as a function and see the y value where x would be 15. But you must remember that that is not a graph of the sequence, but a graph of connected points. So graph of a function of connected points. That is important to remember. Whenever you graph it out in Desmos and connect the dots, it's no longer the graph of a sequence, but a graph of a function. So if you're ever asked to graph out a sequence, just mark the points. Don't care about connecting them, mark the points, that's all you need to do. Now, we have a tricky one because we know that 16 is the 23rd term, and we do not know how far from the beginning and ending we are. So let's see, we have n is 23 and an is 16, and let's just get the difference first. I will use the Pn equation, where P will be 23rd term and n is the second one. But we can make that easier on us since 2 minus 23 is minus 21. We could take one term before that, so 22nd term, which is 13, where the difference is 20, which makes math slightly easier. So let's get the difference between the terms is 3. Now insert in P as the 22nd term, which is 13, and AP, plug in the 2 as the n, plug in the other numbers, calculate them together, so 13 plus minus 20 times 6, 13 minus 60, which is minus 47. So we see that the second term would be minus 47, meaning that the first term would be minus 50, although that is not part of the question, as we only needed this value right here. But this is one way of solving these type of problems. Just determine what is n and what is p, find the simplest calculation, and just roll with it. Like, it doesn't get... It can get more complicated, but we don't need to overcomplicate the problems. We don't need to overcomplicate the problems that already may seem hard. Anyway, next up is geometric sequences, aka the ones that have to do with multiplication and exponents. Basically, it's a sequence where each term is obtained by multiplying the previous term by a constant value called common ratio or lowercase r. Now, for example, let's take a sequence of 5, 10, 20, and 40. We take two consecutive terms, and we see that as all terms don't have a fixed difference, we can assume they have a constant ratio, so we divide any given term with the one before it. Let's take 40 and 20. The ratio is 2. Now I'll give you the formula, which is derived in the same way as the other one was, just through multiplication. So you multiply it by the ratio, which is raised to the power of n minus 1, so the difference of steps we have to take. And again, the general formula, or Pn formula, for the pth term with a common... Oops, I forgot to change d to r. Sorry. Here should be r is the common ratio. I forgot to change that. I do apologize. But yes, we just replaced one with p and we got the explicit formula for the geometric sequence. Now, first example we have to solve is find the 6th term of the sequence 2, 6, 18, and 54. Now, we could just multiply 54 with r 2 times, which is essentially what we're doing, but let's solve it using the formula. 6th term is first term times ratio to the power of n minus 1. N is 6 in this case, r is 6 halves, which is 3. Now n minus 1 is 5, so we will gradually edit this correctly. So we have first term times ratio times, ratio to the power of n minus 1. As you see, I broke the 3 to the power of 5 into 2 times 3 to the power of 2 and 1 3. Because if you multiply them together, you can add the exponents and get 5. Now, this makes multiplication a lot easier, because if you don't know exponent tables, which most people don't, and there is no necessity to learn them, as multiplication can be done by hand fast too, we can just multiply the 3 and the 2 together, we get 6. And we have 2 3 to the 3 squares, we have 2 9s. We have 6 times 9 times 9, which is 6 times 81, which, if we remember the rules in equations, that ax plus bx is equal to x times the sum of a plus b. So let's take 80a as a and 1 as b. We're multiplying that by x, which is 6. We can add these two together or break them apart. So by that rule, we can just multiply 6 times 80 is 480, and 6 times 1 is 6. We get 486 as the 6th term. There's a lot of 6s, god damn. It's a big number, but it's nothing too hard for us, right? Now, example number 2. Find the first term of the sequence 16, 64, 256, 1024, if the 256 is the 6th term. Dear lord, there's a lot of 6s in here. Anyway, let's do this the same way we solved the example number 2 in arithmetic sequences. Get the formula, the Pn formula of course. Ratio is 64 divided by 16, which is 4. N in this case is 1, because it's the first term. 6th term, so 6. Now we paste in the numbers and the values. We get 256 times 4 to the power of minus 5. Now we have fractions. So let's solve 4 to the power of 5 first. So it's 4 times 4 is 16. 16 times 16 is 1024 to the power of minus 1, which we still didn't account for. And now, since 1024 is to the power of minus 1, is the same as if it was a fraction shaped as 1 divided by 1024. So let's rewrite it in such a way, where we multiply 256 with that fraction. But now we see something very fun, or interesting, or cool to see, and helps us solve math if we have big numbers. 256 and 1024 are two consecutive terms. So that means that 1024 is r times bigger than 256, meaning that if I have the inverse of that in this case, so instead of dividing the greater one with the lower one, we divide the lower one with the greater one, the result would be 1 over ratio, which is 1/4, which is 0.25, being the first term. So sometimes you may run into examples like this, which will save you a lot of time, especially if big numbers are hard to divide and find common factors for. Now, let's solve the recursive forms. For example, arithmetic sequence 4, 7, 10, and 13, where the difference is 3. Recursive form is essentially this, so the nth term is previous term, so n minus 1, n minus first, however you want to call it, plus d, the difference. So in this case, nth term is its previous term plus 3. Now for the geometric sequence example, we have 2, 10, 50, and 250, which gives us the r is 5. And we just multiply with the ratio, so the nth term is the previous term multiplied by 5. There's not really much about this. Like, it's easy to also convert back by, for instance, here, we have the ratio, we have the p term, so n minus 1 can be treated as p term, and we have nth term, so we just plug in all the values and we just calculate whatever we needed. So it's really not that hard to convert between the forms. Now, let's cover the other sequences that I also mentioned, like alternating sequence. So these are of course the simple cases. You can also run into some more complicated ones where the entire nth term is multiplied with minus 1 to the power of n or something, which would give us every second term being positive while every odd term being negative. But that's not always the case for alternating sequences. So in this case, if we have an n minus 1, if we have an odd term, so the term placed in a position of 1, 3, 5, or so on, when we take 1 away, it's gonna be an even number, so negative number to the even power is a positive 1. So the terms at the odd position will be positive, and the terms at an even position will be negative. From this formula, of course. That's not always the case for alternating sequences. You can also have terms jump plus minus 1 from some numbers or other numbers, which could be like a sequence of 79797979 that is described as 8 plus minus d to the power of n, or something like that, where you just add or subtract 1. This is technically alternating, but yeah, there's a lot of them. This is just one of the possible formulas, as there's a lot of cases and it would be hard to generalize all alternating sequences with just one formula, while at the same time making it understandable to newcomers in math. So let's go ahead and see what this formula in specific would give us. So let's assume that the first term is 1 and the ratio is 2. Imagine this being our chosen coordinates, and this just describes the map. But yes, first term is 1, r is 2, and I'll be filling in the terms 2, 3, and 4. So, second, third, and fourth term, I plug in the first term, I plug in the n and r, I calculate that, since 1 multiplied by anything is the number itself. We get minus 2 to the power of 1, minus 2 to the power of 2, and minus 2 to the power of 3. And I just solve them, which gives us minus 2, 4, and minus 8. So we see that the second, third, and fourth term are these ones, giving us a sequence of 1, minus 2, 4, minus 8, etc. Of course, this is one example, and there are plenty more. Some we will run into in our next lesson, some you will see in the mini-test, some you will run into in your life, but they're fun to encounter every once in a while. Next up is the Fibonacci sequence, the one I mentioned before. It's a very special case, which I have already mentioned before in this video, maybe even in previous ones. And the Fibonacci sequence is the one that appears in so many different fields that I could make a whole lesson or just a fun fact video about it, and it still wouldn't cover everything, or maybe it would, depends on how long is long enough. But this is essentially the formula for the nth term, the recursive formula at least, and it's just the sum of the previous two terms, which makes it easy if you have a given segment and you need to find previous or next terms, but it's absolutely useless if you want to find the nth term directly if you're not in the right area or the segment. Of course, this is due to needing two previous terms, and since we don't have them, it would be impossible to get something like a 50th term from the first 5. Of course, you could go there, but it would take a while. That's why it is possible to convert this form from its recursive form into an explicit one. Unfortunately, that is quite a lengthy and slightly complicated process, especially to explain it on a PowerPoint. Plus, me personally, I had it in university, which means that most of you will never see this at all. So I don't think it's important to cover it, as Fibonacci sequence is something that one can have as a hobby and explore it as much as they want to on their free will. But I will leave you with this, the name of it, so you can look it up for yourself and do the conversion between the recursive and the explicit one by yourself again under the guidance of the internet geniuses. But the explicit formula is called Binet's formula, and it's a giant fraction with roots and exponents and everything. As you can see, it's not the easiest one to remember, and it's even harder to get with like zero knowledge beforehand. So yes, my point from of mentioning this sequence is that this sequence is very important in nature and science, as it can be found in many different things, like arrangement of petals on the flower, the spiral patterns on the sunflower seeds or pine cones. In computer science, it's useful for algorithms, for instance, and used in tasks like searching and sorting. In arts and architecture, it's used to create aesthetically pleasing proportions and compositions, and so much more. But it's important that this is neither arithmetic nor geometric sequence, because there isn't a constant ratio or a constant difference between the terms, like many other that you may run into in your life. Arithmetic and geometric are just the most common ones that you will run into. Now, next up are the upper and lower bounds, which are quite important later on in the lessons, but now it won't hurt to do a small introduction, as this is the perfect time to do it. So first, let's see why would we even have this. Well, sometimes it's important to know if the sequence stays within a certain range, but first let's see what that even is. So lower bound, marked with a small m, is a number that is, well, it's the number that the sequence never goes below. That means that if we have a sequence that only increases and starts off at 1, a lower bound would be any number equal to or less than 1, since the sequence never goes under it. There's also something called exact bounds, which is the exact lowest or the exact highest value that the bound sequence has. But for the sake of learning, let's remember that anytime I refer to a lower bound or the upper bound, I mean the exact one, even if I don't say it. It will also save you time on the exams. I technically passed my math class in the university purely on this technicality because the teacher didn't specify the exact lower and upper bounds, they just said the lower and upper bounds. So I just did the numbers. I found out that the sequence is falling, like descending from some value, which was a fraction, which I was still able to calculate. So I just set it at the random value that I knew was higher. For instance, if the fraction was 263 divided by 114, I knew that it definitely doesn't go above 5. And since it's falling and I know that it cannot be negative, I can set it as 0, even though that was technically also not correct because it stopped falling at a higher value. But that's just overcomplicating it. The teacher acknowledged their mistake and they gave me enough points to pass, so they were kind of pissed about it because they did mean exact, but they didn't write it. So some teachers that are not at university may not care and just mark it as wrong because their ego forbids them from doing it. But at university, people are chill enough to actually admit when they're wrong, at least at our university. So yeah, always assume the exact lower and upper bound, even if it's not specified. It will save you so much more trouble. And if you really don't know, you can always eyeball it and just play on the words and say that they didn't specify exact, okay? It doesn't hurt to learn. Now, the upper bound is, as the opposite name suggests, capital M, number that the sequence never goes above. So again, upper and lower bound, we refer to the exact bounds. So we have the highest value that the sequence has and the lowest one that it can have. Nothing in the sequence is above one or under the other. Now, for the example, the nth term is described by the formula of 1 over n. So let's plug in the numbers. Now, I guess that PowerPoint likes halves and quarters a lot more than other fractions since it automatically corrected them in this form. But anyway, we can see that we started with a 1 and the numbers keep getting lower and lower and lower and lower and lower. But the question is, how low will they go? We can use the graph for that. I do apologize for it being confusing, but if you were to zoom in, you would see that this red line never crosses under 0 or doesn't even touch it. So that we know that if the graph is falling, that 1 has to be the highest value, so capital M is 1. And we know that 1 over n cannot be negative as long as n is a positive number, since it cannot be 0, as no matter what you divide by, a non-zero number divided by 0 cannot be 0. Also, anything divided by 0 is basically undefined in this context. But best we can do is approximate. That's what limits are for, and that's a whole separate lesson after functions. But for the sake of the example, a limit is essentially the y value that the function approaches when it gets closer and closer to the designated x. In this case, x would be infinity, and we would put that as n. Then we would get 1 over infinity, which can be approximated to 0. So our answer for lowercase m, aka lower bound, is equal to limit of 1 over n, where n approaches infinity, that is equal to 0. We will, technically you would have to know limits before calculating the exact lower and upper bounds, because sometimes these formulas can benefit from limits, as technically you cannot calculate the lowest value that the sequence has, but we do know that it will never cross 0, but it will always approach it. So that's what the limit essentially is. So what's next? This is the end for the lesson, of course. As you can see, it's a lot shorter than others were. But now that we have covered sequences, we are ready for our next lesson, the series, which is basically terms and sequences summed together, followed by functions and limits. And of course, limits will sadly be introduced after that, so we will not learn the full scopes of functions. But I will be using the base definition that we saw today, so that the value of the limit is the y value. that the function has, or it approaches when x is equal to, or at least super close to, which is the important part, the desired value we are looking for. So for instance, when x approaches 3, what would the limit of the function be there? In graphs, this will mostly be either positive or negative infinities as the y value, or 0. And again, the x itself will be approaching either of the infinities or 0. So these are just the general cases. We will cover them when we get to the functions. Do not worry, do not get confused by now. But when we get to limits, we will see some examples where x approaches a specific number and function starts behaving very weird at that specific value while being completely normal everywhere else. And yes, that's about it. Hopefully this lesson was clear enough. I do despise this topic greatly. I never liked it, to be honest. But it is what it is. You gotta cover this and series, as they are somewhat important, I guess. I'm not gonna lie to you, I have not used them once after I've done them with the exams, so... But technically they're not even that complicated. The series are a bit more, so I'll try my best to explain them or make a good video out of them. Other than that, sequences are just pretty much forgotten. You just need to remember the formulas, the PN formulas for both arithmetic and geometric, and how to convert between explicit and recursive, and that's about it. That comes in handy in series, which is next in 2 weeks, of course, the next lesson. So yes, now without further ado, let's get you guys the mini test so you can see if you picked up anything from this short lesson. And unlike on the other videos, I will do some call to action. I do start streaming on Twitch in a couple of weeks. June, for now, it's like that week after 15th of June, I think. Was that like... Yeah, 16th June or forward. Sometime then. Yeah. You can follow me on Twitter/X to see the schedule, whatever it's pronounced at. I will be posting the days and times, so you can try to catch me if you can. And yeah, the stream starts then. I have to set up everything until then, but yes, thank you so much for being here. I would appreciate you if you followed me on Twitch or X so we can talk more, so you can catch me playing games, so we can have fun there together. But again, it's not required, so it's not subscribing to this YouTube channel unless you want to see more of my videos, which I would be very honored if you would. Thank you so much again, and have a good day. See you on our next quest. Bye.